Muy bien, buenas tardes. En esta ocasión, Eduardo Frías nos va a platicar sobre especies combinatorias, un tema que ya tiene, no sé, unos 2, 3 años
Especies
Eduardo
combinatorias.
trabajando con esto. Sí.
Gracias, Héctor.
Adelante.
Voy a hablar en inglés. I'm going to talk in English. I'm going to talk about of combinatorial species and something about of polynomial vector fields. Okay. Oops. I'm going to divide. I divide the talk in 4 chapters. First, I'm going to talk about some clippings from Bergeron's book. After that, I'm going to talk about one example that Art and I are very interesting. And after, I'm going to talk about the precedence of the example. We are working with this source of information, principally combinatorial species and tree-like structures from Bergeron, Lavelle, and Roots. They are Canadians, Franca speakers. I don't know how to say. Oops. Okay. The definition is very strong for understand, but I want to present here. Species of a structure. A structure is a rule F which produces for each finite set U a finite set FU, and produce for each bijection sigma from U to V a function F sigma from FU to FV. For be less abstract, I'm going to think maybe in rooted trees or simple graph, or maybe direct graph, or other of these. I'm going to think in simple graph. Then FU is the set of all graphs that I can construct in with vertex and U. And this F sigma is a function that at each graph on U is sending to one graph and on B throw off sigma. The function F sigma should further satisfy the functional properties that F tau composed with sigma is equal to composition of F tau composed with F sigma. For the identity from U to U, the transport, the function f identity U is equal to the identity over the f U. In the case of the graph, is the identity of on the old graph. Some element of FU is called F structure. In the case of the graph is graph structure on U. The F sigma is called the transport of F structure along sigma. The three next expression S is a structure of a species F on U. S is an element of FU, and S is an F structure on U, are synonymous. We have a definition, additional definition of isomorphisms. If I have two F structure S1 in FU and S2 in FV, and if I have a bijection sigma from U to V, is called an isomorphism of S1 to S2 if S2 equal to sigma composed with S1 is equal to the transport of S1. Is the general isomorphisms in F structures. And examples of F structure, there are so much. The species A of rooted trees, the species G of simple graph, all of these are examples. I don't know, the species N of endo functions, i.e. N in U on U is equal to all the functions from U to U. The last two examples, C and L, are very necessary for the second part of the talk. The species C of cyclic permutation or oriented cycles, the species L or linear or total orders. Those examples, we can define it with certain axioms, but we can give a explicit example, like the singletons. The structure is the set of U if U has a cardinality 1 and empty and otherwise. The species 1, this is the name 1, the characteristic of the empty set defined by the structure one on U is U, the set that contains U, if U is equal to empty set, and empty set and otherwise. There are other important examples. The empty spaces denoted by 0, defined by 0 of U is empty for all U. This species E2, the characteristic of set of cardinality 2 defined by E2 on U is U if the cardinality of U is equal to. This is a explicit examples. We can define implicit example. I only mention quickly here, and forward I'm going to mention again. The rooted trees, I can define it in this way, but it's implicit, but because I use A to define A, the orders I can define in this way, but it's implicit because I use L to define L. I'm going to mention in forward. Before I'm going to talk about associate series. I can associate three series to each species. What is that? I'm going to save the information of the number of elements of each species in a set of n elements. I'm going to have a series where Fn is a number of F structure on a set of n elements, and then I have a series where I save the information about that. We have this series. I'm going to do the emphasis that we have a n factorial here. I have here examples. LX, CX, X, the singleton, the zero species. But I have here some of them that are not serious. What's happening here is that I take the function where the series converge, convex. Here we have the series of G, that simple graph, and the endomorphisms. This is the series of the graph that I can put as a function, permit us manipulate the series in a good way. We have the type generating series. This series don't have a n factorial as the generating series, and this the type generating series save the information of unlabeled F structure of order n, the number of unlabeled of a structure of order n, or the type of isomorphisms is other way to see. And we have the next example. Again, I put only the function where convert the series. There are other series that related or associated to the some F structure that I call, and the book called too, cycle index series. I want to explain very much. I only to say that it's a series in many variables, and it is related to the other two with this theorem. For any species of structure F, we have that the generating series is the series in I forget the name, cycle index series, but with the first variable x in the others equals to 0, and the types generating series is equal to cycle index series, but the first variable equal to x, the second equal to x square x, etc. I have here some examples of C series. The C series of zero species is equal to 0. The C series of species 1 is 1. The C species of the C series of X is the X1. The C series of L is 1 over 1 minus X1, etc. We have some operations about the species of a structure. The first of them is the sum. Essentially, the sum of two species is the union of the structures that is disjoint union, and transport is the transport in each of them. Yes. The theorem about the series is very easy. The series is the sum of the series for obviously motives. The type of series is the sum of the types of series, generating series, and the C series is the sum too. This is a manner of counting. For example, is I have the even set species of a structure and the odd. The even is hyperbolic cosine, and the E odd is the hyperbolic sine, and the sum is the series of E. And this is the generating series. IE is the example of this. This is the type generating series, and this is the Z series example of this. Then we have the product of a species of a structure. Essentially, I have a partition of U. This is the union of U1 and U2 is equal to U, and the intersection of both is empty set. And I have the Cartesian product of the structure type F on U1 and the structures of G on U2, and I have the union of all of them when I take all the partitions. This is the product of the species of structure. I have transport 2 for each sigma, and I have a product theorem about the series that is simple. The series of product is the product of the series in each of the series for the 3 series. Example, if I have the series of the all permutation, and the set series that is EX, And the series of all permutation that don't have a fixed points, then we can calculate with the previous theorem the series of all permutation of that don't have a fixed point. In the next way, the series of S is 1 over 1 minus X. The series of E is E power X, and I want to have the arrangement, the series of the arrangement, the species of permutation that don't have fixed point. And using the theorem, previous theorem, we have this, and I only need to, I don't remember how to say despejar in English, sorry. And I have the counting of the arrangement. This is the series in generating series. This is the generating series of types, and this is the cycle index series. Okay. We have a substitution of species structure that we need three things for the substitution. I need partitions in partition P of U, and I need phi structure on the partition, and I need gamma P structure on each element of G structure. I have here a scheme of that. The F composed G structure in one set. First, I have a partition of U, and then I have G structure in each cell, and I have F structure on this set of classes of P. Yes, this is the scheme. We have a theorem about of composition. For the generating series is very easy. It's only the substitution of the series. For the types is very much complicated. Is plentistic substitution. Is C series of F, but where we have x1, I need to put the tilde G of X, and where we have x2, I need to put G tilde of x2, etc. And this series in cycle in this series is very much complicated, but is that And I have here one example. The species of endomorphism is S composed with A. And we have here the series. Okay. The most important thing is that the series operate as a species operate. Then we must consider equation of species, then pass them to equation of series and finally solve them as a form of counting. And I'm going to put again the examples of implicit series. I have the rooted tree series. Then I have A equal to X point product to E composed with A. Then I can solve the equation to count A. The L series is the same. If you remember, when I have, I'm going to annotate. For example, this is the most easily. If I have the series, I only take this series because the series is going to do the same that the species. And I can put this. Then I can factor 1 minus x, this x equal to 1. And I have this series. Very quick. It's one way to obtain the series of Lx. I can do this, but this is I have a quadratic, but I have little time. And I continue. Oops. Then I'm going to define, I call BPWB3. It's a bicolored planted tree with the restriction that that there is no y vertex next to y vertex. The degree of y vertices is a lead trees. And the question is, how many of these three are there? With 3 black vertex, I have 2. One with only black vertices, and one with 1 white vertex and 3 blacks. This is this number. 0 white, 0 3. 3 black vertices, 0 white vertex. With 4 black vertexes, we have 4 trees. 2 with without y vertex and 2 with 1 y vertex. This is with 0 y vertex and 2 with 1 vertex. With 5 vertex, we have 3 without y vertex and 4, 1, 2, 3, 4, 5 with 1 y vertex and 2 with 2 y vertex. This is 3 with 0 y vertex, 5 with 1 y vertex, and 1 with 2 y vertex. If you remember, y vertex, the degree is at least 3. This is restriction. I think I want to check the motivation, but it had related with polynomial vector fields. And the counting with this cardinality of black vertices and this white cardinality of y vertex is that we work with this theory that I present in the first part, and I'm going to say how this result is with Arduino. That here is he. He is here. He is from El Paso, of UTEP, University of Texas at El Paso. We need the series of linear, of the cycle species, of the sets, of the singletons in the pairs. This is the basic series that appear in the book that we by basings. We need the cycle index of this series is the C series or the cycle in the series of C, but at least n vertex is the same of the cycle minus these 3 terms. We have this lemma, the species E2 over A plus B is the species A2 over A plus A2 over B plus A product to B. And we need to define species of 2 sorts, because I have 2 types of vertices, y vertices and black vertices. Then the name is species of two sort. Two sort species is a rule F which produce for each finite two set is the name of when we have two kinds of vertices or elements. Finite two set, a finite set of U. For example, the set of the trees that I mentioned before. And we need a transport sigma that is functorial too. And I have two kinds of singletons. Xi equal to U if the cardinality of U sub I is equal to 1 and U sub j is empty set. For I equal to 1, 2 and j equal to 2, 1, inverting. The Z series, we need to change instead of x1, x2. I need two sets of infinite variables. x1, 1, x2, 1, 2, etc. x2, 1, x2, 2, etc. And the cycle in this series is more or less than that is. Then we have the theorem A in this form for generating series and for the series of types. We have the theorems for the sum, for the product, for the composition, but for the composition we have a special because we need to combine one sort species with two sort species, and the theorem take this form. Oops, ¿qué estoy haciendo? Okay. Then I repeat the question. If I have a bicolored planted tree with restriction that there is no y vertex next to y vertices, the degree of y vertex is at least 3. How many BPWP trees are there? Okay, we need to construct the equations. I call y1 trees with ordered branches and white black root. Black root is I related with the subindex 1. Then y1 is equal to x1 with ordered branches. This is the class, L is the class of ordered. And y3 is the sum of y1 and plus y2. Y2 is the trees with ordered branches and white roots. Then y2 is equal to root x2 and branches of kind y1. Why y1? Because y2 can't have vertices with y vertices as a neighbor, then only can put branches with black roots here. Yes. After that, the y tree is equal to y1 plus y2. That is the equation. And I have the equation with only y3. Then I change to the series, and I have an equation with y3. Here L is the series of L, and it is 1/1 minus y3. Then I substitute, and I have y3 equal to this, an implicit equation on y3. Then I multiply to this factor, and I have this equation. When I solve y3, is a cubic equation on y3, I have the series of y3. Yes, that is this, where D is this. The y4 planted trees, this is when we put in the plane, Euclidean plane, affine plane. We have this equation, rooted with black vertex and rooted with white vertex. And after that, we have a multi-sort symmetry theorem in this form. I don't have time to explain. And then we have this symmetry theorem applying for our case, and I have this. Then we have that y5 tilde is that when I put in the series. After that, having y3 and having y4, we developed the Taylor polynomial, and we obtained this table. In this moment, we are looking for explicit formula. In a future talk, maybe we are going to talk about. And I only want to say a little about the motivation of this example. No, I'm going to polynomial. Is I have this polynomial vector field. If I take the phase portrait, we have two things here, two basins here. And if we have, if I rotate with I, we have this other portrait. This is a polynomial vector field on the Riemann sphere. Then I have a little time. Then we reserve a region for this basin. We reserve some area for this basin, and I reserve an area for this basin when I convert to center. This zero, I reserve this area and reserve this area, and then I have 4 areas for each basin: the left, the right, the top, and the bottom. This is my black vertices, and in the middle I have something like a square, and this is my white vertex in my example that I explained before. And the idea is count these topologies of these things. I think I don't have time for more, and then we only have 4 minutes for questions. Then I'm going to give time for question. Do you have any question?
¿Alguna pregunta? ¿Apenas te hiciste trabajando con ese tema, Eduardo?
Sí, la tengo trabajando con pues de las cosas más básicas, de pues explicar un poco la definición, explicar algunas de los ejemplos de aquí, y que calcule unas series como explícitamente. Entonces, sí está de licenciatura. Bueno, no sé, ¿alguna otra pregunta? Any other question?
Bueno, pues damos las gracias a Eduardo por esta plática.
Gracias.